update on the loop antenna after experimenting with different feed points in the tap feed method, trying to get optimum performance, because for some reason this loop is not radiating much signal compared to what I can get radiated from the railing of the balcony. So something's not quite right. The match can be good. Let's have a look at the loop. So here it is, and what I've done is I've tried different tap points here, here, and here. I've also tried 3 different lengths of coupling loop, 75, 100 and 125 centimeters, and also 2 different shapes, either as circular as possible hanging down or scrunched up to try and increase the coupling from the small loop to the large loop. So that's quite a lot of different combinations that I've tried. And if I look at the results, here's the diagram with those different points. I haven't tried this one yet, point C. Maybe that one comes next. But looking at each of these, the points A, B and D on that diagram, and measuring only at 10, 14 and 18 megahertz now, you can see that I get the range of the SWRs. The best one on 14 megahertz is 1.0. That's the 100 centimeter coupling loop, which is what I started with. That was the initial guess. Connected to point A, and point A is up there, not D, because when you move to D, things get worse. That then drops to 2, as in drops in quality by increasing from 1 to 2. So as you can see, it makes some difference. Also, if I make the loop more closely coupled, less circular, then I still get 1.0 SWR, and these numbers show that it's shifted slightly lower in frequency by doing that, the resonant point. So there's a whole range of different VSWRs. Obviously I want the best, like 1.0. The problem is the loop just doesn't radiate compared to the balcony railing antenna, which I tried a few videos ago. That's this railing along here, which I connected through a dual wire line with the bottom half connected to the other railing. That gives far better performance on FT8. When I look at the map of where my signals are being heard, it makes a huge improvement, even though it's not the best antenna in the world. So this loop is not performing how I would like it to yet, but that's part of the fun, isn't it? Trying to optimize things. And possible causes of low radiation features is that there could be high resistance around the loop because there are joins between these sections. They just push into each other and there's a clip, just like tent poles in the old days of putting up tents. So there is some resistance in there. There's also, of course, some resistance with these connections here to the capacitor, which I've tried to keep low, but it's probably not perfect. I hope this brass is a good conductor rather than copper. Maybe I should swap that out. Also, having the foam on the loop may damp things down a little bit. So I've got 2 options to reduce the electrical resistance of the whole loop. I could put aluminium foil around the outside, which I did on another antenna that I played with, and that one works extremely well, where I use plastic drain pipe with aluminium foil stuck around it, the one that comes in a tape, and that worked very well, much better than this one. So maybe I'm going to try that next, wrapping foil around here somehow for the whole loop to reduce resistance. The other thing I could do is take that off and then take off the foam and see if it works better with no foam on it, in case that's damping things down. Because this loop does show quite low Q and quite wide bandwidth because of that, which is unusual. These loops normally are just a few kilohertz wide on tuning, and this one is hundreds of kilohertz wide, so it's showing a low Q. There is a tool on the internet, a very nice tool, where you can put in all of the design parameters here, and you can then see what's going to happen. And the resistance has to be in the range of milliohms, and of course that is hard to achieve, such low resistances. So there's a few variables for me to play with, and I'll have a look at the calculator for loops on the internet. Different loop calculators I can try. The first one is quite complex and gives a graphical output, and the second one gives him a numerical output, looks a bit less complex and much easier to use and to understand. This is the easy one. This is on a website called 66pacific.com, and you can look on there for the transmitting loop antenna calculator, and it's nice and straightforward. I had to change the language somewhere. There's a language setting. Oh yeah, you can either have the language set to English or metric. I'm not going to comment on that because I'm staying politically correct, but I like that. Maybe, no, I'm not even going to go into England and the USA. So there we are. I set it to not English but metric, so I can put in meters and centimeters. So the circumference of the loop I just showed you is 2.7 meters, and the diameter of the conductor, that's the aluminium tent poles inside the foam, is 2.2 centimeters, and at a frequency of 14 megahertz with a transmit power of 5 watts. Actually, it's not going to change anything putting that in, but anyway, press calculate, which I did, and it shows an antenna efficiency of 54%. I think I'm getting a lot less than 54%, way less than that. Bandwidth should be 14 kilohertz, which is very narrow because, of course, it's a high Q, theoretically almost 1,000. Mine has a bandwidth, as I said, 10 times more than that, so maybe the Q is a lot less due to resistance. The 5 watts results in a current of 5 amps circulating, which doesn't change anything. What's important though is the loss resistance, which has to be low. This is 38 milliohms in theory, but I think mine might be a lot higher, which is causing the problem. And if we go to the other website, the more complex one, up here, this is this URL, Miguel Vaca at GitHub. You can have a look at this, and this is a little bit more comprehensive. It's got a lot of maths in this, and what you do is you adjust these sliders here to enter the parameters for the loop, and there's a key to tell you what each of those parameters means, those variables, so you can enter those, which I did. And this is the loop, so I'm transmitting 5 watts, and I've estimated the resistance to be 200 milliohms, which is a value that is true for a fairly good loop and a little bit higher above ground, but I'm sure mine is not as good as this. And 22 millimeter pipe diameter. The diameter of the loop is 89 centimeters because of the length I put in. It's a single turn loop, so n is equal to 1. And it's got an area, cross-sectional area. Just saw that, 0.6 square meters. And if we look at the graph, we see a lot of curves which show various things like what capacitance is required, what voltage will appear across it. That's the green and the yellow curves. What bandwidth will you get? What will the efficiency be? And so on. The resistance of the loop, the yellow one's important because these are all theoretical values if everything is done properly. And what happens is if I adjust the resistance, which I set to 200 milliohms, this RE slider, if I slide this around, you see what happens to these curves. It makes a very big difference. Very quickly, what's happening is this brown curve rises as I increase the resistance, and the brown curve is bandwidth. So having a higher resistance in the loop gives a wider bandwidth, which might sound nice, but it's actually indicating it's a worse loop. The other thing that happens as I change the RE, should be the Q changes somewhere. Yeah, this one here, this purple line which is going up and down is the Q. So when I have a low resistance, that's currently 0, the Q is quite high. Can't see here's the Q scale, it's 2,500, nearly 3,000 the Q, huge number. And then as I increase the resistance slider down here, you can see that purple curve goes down very fast and the bandwidth starts rising. So when I get to the 200 milliohms, which I think that I might have as a rough guess, which is here, oops, go away, oh no, so 200, no, try again, that's 0, 200 milliohms, I right-clicked by accident, that's 200 milliohms. You can see that the curves change quite a lot. I'm looking for the purple one, that's the purple one, that's the Q, says it's, well, let's go to 14 megahertz, which is around about here. So the purple line, which is the Q, gives me a Q of 626 in theory, which is reasonably high. And the bandwidth ought to be, what does it say? 22.8 kilohertz, which is quite narrow, which is what you expect from a loop like this when it's performing properly. But my loop has a much wider bandwidth than 23 kilohertz. In fact, if I increase the resistance even more, so the bandwidth gets wider and wider, let's see how wide that can go. The bandwidth is the brown curve. You really have to get used to using this graph, but I like it. Where is the brown? Can't see it. Anyway, if I just put the cursor around 14 megahertz, what does it say by the brown number? 64.8 kilohertz. It's still narrower than my loop, so my loop is performing even worse than that. And there we're with a resistance of 757 milliohms. That's 3/4 of an ohm, and I'm sure mine's even higher. And this, of course, is not the DC resistance you'd measure with a multimeter. This resistance is the RF resistance, the equivalent resistance to a high-frequency field, or current flowing, and that depends on the skin depth. And the skin depth you can calculate in microns, but we won't go into all of that right now. So let's have a look at 14 megahertz again. With 1 ohm, then the bandwidth would be 82.6 kilohertz next to the brown box. And I think mine's even wider than that. So it's hinting to me that the resistance of my loop is way too high. And it's even higher than this maximum here. And of course, optimally, it should be down here somewhere. And you can see as you do that, the bandwidth decreases and the Q increases. Wow. So I'm going to have to go back to the drawing board and try a different way of constructing my loop to have low resistance. Now I'm happy again. Finally got it working properly. Took most of the day, but now I'm getting results. And what I did was I put foil around that loop. That's a pigeon. Probably fried it. Yeah, the foil is 100 millimeters wide, and that's 22 millimeter diameter. Tube, no, it's not. It's more because of the foam. I left the foam on, so it means that when you wrap the lengthwise foil around, it leaves a gap, which I did. Put the foil on the inside with a gap on the outside, small gap, and then I put foil on the outside with a gap on the inside to cover it over. So it's actually 2 layers of foil, one on the inside of the ring and one on the outside. But it works, and I played around with matching, of course. I've kept the capacitor connections the same, that is using the 2 different stators of the 2 capacitors and nothing connected to the rotor, which means that those 2 variable capacitors are connected in series. And it works at 14 megahertz. The bandwidth is incredibly narrow, which is what I was expecting. That shows it has low resistance now. The feed at the top, I was playing around with the tap matching, which I used on my square loop, which is where you connect the ground of the coax to the loop somewhere near the center up there, and then you have a piece of wire and then clip it somewhere around here to get a good match. That's just not working on this antenna, and it turned out I gave up using crocodile clips because it was too slow taking the wire on and off, and instead I'm using this monster clip instead, just so I can quickly move it around. I found the best spot was to connect the end of the loop here, right next to the ground from the coax, so the loop now goes around and all the way back to the same point. In fact, it probably doesn't even need to be connected to the main resonant loop now here. Probably I can have an independent loop with a coaxial connector, which I'll try tomorrow because I think I need a rest today. But now it's working, and I found the best arrangement is to have a fairly small distance between the feed loop and the main loop for a while, and then let it droop down and go up again. So it's in the kind of in the top right hand quadrant if it were square, with some closer coupling, and that gives 1.0 SWR, 14 megahertz, very nicely. But now it's incredibly difficult to tune with that capacitor. You just have to walk near it and it goes way off tune. It's super sensitive, and if you put your hands anywhere near these sides, then the SWR shoots up. So it has an extremely narrow bandwidth. It's just a few kilohertz, which is what I'd expect from looking at that graph on that interactive website. The graph showed that when you have a very low resistance, you're going to have a very high Q heading for 1000, and the bandwidth of just a few kilohertz. And I think that's what I'm heading for now. It's a huge difference. And I have got it transmitting. It's sending at the moment on FT8. So if we go and have a look, let's see where the signal has been received. So there's the FT8 transmission. Oh, it's gone into, back into receive mode. There is the map on PSK Reporter. Nothing in the USA yet, but I think the band is fairly close. And you can see the darkness is coming, so I need a break. Yesterday I was doing this till after midnight, playing with that capacitor. Anyway, now I'm getting signal reports. Where am I? In here somewhere in Germany. And now I've got one report from up here, which is in Estonia, which is, how far away is that? 1,500 kilometers away in Estonia. I've got what is the report there? It's probably very weak, minus 19 dBs, okay. At least it worked. I've got here in Russia, minus 18 dBs from over there, and that is 1,940 kilometers away, which is not bad. Only running 5 watts. So this 5 watts is going quite a long way. And down here I've got, where is it? There, that is Malta with a signal strength of minus 16 dBs, 1,400 kilometers away. And then various stations in Spain have received my FT8 transmission, minus 17 dBs, minus 15 and minus 19. So it's fairly consistent. Not the strongest signal, but at least there's some propagation now. The next thing to do, of course, is before the band conditions change, is to switch back to the other antenna, the balcony rail antenna, which works incredibly well for what it is, and to see now which is better, that antenna or the loop. So I'll probably try that next. Let's see what happens. Remember to like and subscribe. I do it all the time. I couldn't resist the temptation. I've switched back to the balcony antenna, not the loop. So now it's this long metal railing that's the antenna, fed through this twin bell wire line. And I'm comparing it to the loop antenna before the signal conditions changed too much on 20 meters. And let's have a look and see what I've got on the PSK Reporter software website. So zoom in a bit. Everything that's like 34 or 35 minutes ago was on the loop. That was that station in Russia, is the furthest, nearly 2,000 kilometers away. And the more recent reports now are using that balcony antenna. So there's one here just 4 minutes ago, and that is Bulgaria with a signal strength of minus 20 dBs, which is comparable to the loop. I think minus 19 was the weakest, so minus 20 dBs into Bulgaria. And then that was the loop. Malta, we saw minus 16 dBs. Now I've got a signal report from here in Italy. And what does that say? That is minus 18 dBs. So it's very similar signal levels to the loop antenna. Here in Spain, minus 7 dBs. That's the strongest signal yet. And over here in the west coast of Spain, minus 19 dBs. Okay, that's the same ballpark. So most of the reports I get are about minus 16 to minus 20 dBs on either antenna. They seem very comparable, and they're both going into Spain and then Eastern Europe, Latvia, Russia and Bulgaria for the other antenna. So actually they seem to be quite similar now in coverage, and this was the strongest signal here with minus 7 dBs into Spain, the northeastern corner, which is not too far away from where I'm in Germany. So there we are. So I'm happy now that I've got two antennas I can compare, and they're both performing properly, and they are both homemade antennas on low budget and not too easy to see from outside. I think the loop might be, but I'm going to have to say it's something for birds to sit on because I'm a nature lover or something. Let's see what happens. But there are more antennas coming. Tomorrow in the post I'm going to get an antenna which is probably only this big, and we'll work on HF and VLF as well. Receive only, but maybe I use the low noise amplifier part of that in a loop which is not tuned, and see if I can get something working like the Wellbrook loop antenna, which is an incredibly good antenna for receive only, very low noise, and it goes right down to something like 50 kilohertz, where it's interesting to listen to those maritime beacons and aeronautical beacons. So let's see what the postman brings tomorrow. There's quite a lot of stuff arriving today and the day after, so there'll be some things to experiment. So now it's good night from me, and I really am going to stop this now. Thank you for watching, and please make comments, questions, criticism, whatever you like, suggestions, things to try, and solutions to my problems, and hope to see you again soon. Bye-bye. Just before I go, there are two things I wanted to say, which I almost forgot. And one of them is, in a previous video I was playing around with USB leads with ferrite noise suppressors on them, and found the best way of suppressing noise, because I was having a problem with noise from the computer getting into the radio. I also had problems with wsjtx crashing. And I think the problem was a wobbly USB plug, because occasionally you get that awful Windows ding 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 sound as something got disconnected, and then an error on the software. So I thought, let's change the USB cable to a different one, maybe it'll fit the plug better. Some of these things are not very well made, not the best fit, and this one doesn't have that intermittent electrical problem. But not only that, it also doesn't radiate any noise or conduct any noise from the computer into the radio like the other cable did, the black one. This one came from Samsung, I think, for a mobile phone. So obviously the white cable is much better shielded, or there's something better about it than the black one, and it doesn't need any ferrite blocking on it, which is interesting. I'm quite surprised. The other thing I've discovered is this radio is transmitting 5 watts on FT8, and it's getting too hot to touch, painful. You can burn yourself on it only after a few minutes of use. So it needs a heatsink, so I've ordered one, and probably I'll show how to fit that when it comes, and see if it helps with the heat problem, because at the moment I don't want to run this radio too long, because I don't want to break it. I keep having to switch it off to cool down. Okay, so good night from me, and talk to you all again soon.